So in the previous video, we looked at this particular structure. I'm going to go ahead and go straight to the chair. And we said if you want to do an E2 elimination on this molecule, cyclohexylbromide, actually what you're going to need to do is have the chair flip to where the bromide is axial, and that sets you up to have a beta hydrogen that is anti relative to our leaving group, and then that will do the E2 elimination. This one probably can't do any E2 elimination because the beta hydrogens are not anti to the leaving group. Now there's a little bit of a problem with this because actually this conformation on the right should be higher in energy. It should be less prevalent than the conformation on the left because this one has an axial bromide, and that introduces steric hindrance, and so you would expect this equilibrium to favor the starter material. So this might actually slow down the rate of the reaction because the molecule can only react through a less populated conformation. Okay, now let's take this a step further. Let's look at another structure. This bromide, barely different. All we do is add a methyl group. Now, if you notice, if we want to do an E2 on this, we're going to have a difficult time because if we look at the beta hydrogens, the beta hydrogens are not anti. So there's no anti beta hydrogen. Well, we fix that in the top example by looking at the flip chair. And to do this, we'll flip this. Now this methyl group is equatorial down. It will now become axial down. And this bromide will become axial up. And that's a good thing. Now we have our halogen, our leaving group in an axial position, and there's an axial beta hydrogen next door. So that's a beta hydrogen. And so now our base can find an anti-beta hydrogen, and we can kick out our leaving group. And that'll lead to our expected product. Now I'm going to just draw it with an alkene in there. What the heck? Okay, bam. Now, if we thought this top example had a problem because we said, uh-oh, we got to put this bromide in the axial position and that's less favorable, look at this lower example. Now we're putting not just the bromine in an axial position, but the methyl group in an axial position. We're putting two groups axial, which is at least going to double our steric repulsion. Based on this, we would expect this top molecule should react faster, and the lower structure, this reaction is going to be slower because we're having to go through this much less stable conformation to get the reaction to occur. So this requirement to have anti-beta hydrogens relative to your leaving group really is a significant restriction upon whether these reactions can or cannot occur sometimes. And notice, if we just drew this molecule as flat, you'd have no problem with this. We really ought to show this. So these are technically trans. So that would be up and that would be down. You'd say, oh, no problem, Dr. Stevens. I'll treat this with sodium hydroxide and we'll get the elimination and it'll go without a hitch. Well, as it turns out, when we look at this from a conformational standpoint, this E2 elimination is not nearly so easy. It can happen, and it can happen going through that conformation, but we are requiring the molecule to adopt a high-energy conformation to allow the E2 to occur. So this anti-restriction for our beta hydrogen leaving group really imposes a whole nother layer of complexity upon the E2 reaction.